heat dissipation of erasure.
Thank you. Okay, good morning. This is work done in collaboration with my student studies and Google Research and my PI, Yasser Omar, at Instituto de Telecomunicações in Lisbon, Portugal. So, as the title would suggest, this research basically falls on the domain of quantum thermodynamics. Maybe I should put quantum information erasure here to avoid any confusions. So, so in the overview, essentially, first I'll go over briefly over Landauer's principle of information erasure and its translation into the quantum domain. Then I will argue or go over the argument for how you can characterize the equivalence class of the optimal unitary operators for minimal heat dissipation given maximal probability of information erasure, which I will define shortly. And then at the end I'll go over how you can get a trade-off relationship between the probability of information erasure and heat dissipation, whereby an increase in one will also be accompanied by an increase in the other. So kind of a dynamical variant of Landauer's principle, perhaps. Okay, so Landauer's principle, essentially, how many of you are familiar or not familiar with Szilard's engine? Okay, I will explain it. Okay, so consider, if you will, a box, with a single gas particle inside, and then it's in thermal contact or thermal isolation with the environment at temperature T. And then you place a partition in the middle of the box, and then you make a measurement to see which side of the box the particle is found on. If you find it in the right side, you attach a pulley and string with weight mechanism to it, such that as the particle is allowed to quasi-statically expand, the weight is elevated, thereby increasing its ordered gravitational potential energy, which you can then use to do useful work later on. And of course, you do the same thing in a symmetric way, where you define the particle in the other side. And the work you get is simply just given by this equation here from classical thermodynamics, which is kT log 2. And then, Szilard basically used this example to try and exercise Maxwell's demon by saying that, here you're kind of violating the second law of thermodynamics. You're using heat energy and converting it fully into work without affecting any other change in the universe. And so initially they said, well, obviously the measurement process itself must cost at least kT log 2 units of energy. But later on, because there were examples proposed where you could actually perform the measurement process in an energy conserving manner, said, well, an argument proposed by Landauer, Bennett, and I think Oliver Penrose, where they said, well, if this Maxwellian demon, which is performing the measurement, is itself a physical system with memory, which is finite, then you could explain away or this violation of the second law of thermodynamics by saying the erasure of memory in the demon is costing kT log 2 units of energy. Because again, this amount of work is extracted after in many repetitions of this cycle. After each time, the demon has to erase its memory so that it can record the position of the particle at every cycle. And so what we call information erasure in the demon is basically a irreversible or many-to-one mapping on the different configurations that its memory could have to one assigned state. So here in classical physics, you say it's a mapping from the configuration space to one state only to one. And so here Landauer's limit says that basically delta Q is the heat transfer to the reservoir, beta is the inverse temperature, and delta S is the entropy reduction on the system, the memory. So it's positive if you reduce the entropy. And this relation holds based on Landauer's principle. In quantum physics, this naturally translates to saying a many-to-one mapping on a Hilbert space, where you want to prepare your system or your memory in some defined pure state phi 1. And there's a generalization of Landauer's principle by David Rieb and Michael Wolf in this paper here, where they say, well, there's a correction term based on the dimension of the Hilbert space for the reservoir, such that as dr tends to infinity, you get back the original Landauer inequality there. Now, one thing, and here's the framework for information erasure in the quantum context. So you have your object of information erasure, the system whose information you wish to erase, called O. And these are the different, the orthonormal basis which expands its Hilbert space. And here is the reservoir system, where the energy increases as you go from 1 to dr. And it's initially prepared in a thermal state. So people ask me a few times, what is a thermal bath? I'm not going to answer that in any deep philosophical way. I'm just going to say it's given by a Gibbs distribution of the energy levels, and leave it for other people to explain more depth. And so, yes, the reservoir has the Hamiltonian HR, which you write this way, where the energy levels lambda m are listed in non-decreasing order. So it increases as you go up the index. And the object and reservoir are initially uncorrelated. So the state of the total system is rho object tensor the thermal states of the reservoir. And the two evolve by some unitary operator. And then the heat you define as the increase in average energy of the reservoir. Of course, that's not such a innocent claim, because if when you say heat is basically the energy you define as being something that's lost irrevocably and cannot be extracted as work later on. And this would require that the state of the reservoir remain thermal after the operation. Of course, if the reservoir has a finite dimensional Hilbert space, then in general its state will not be thermal, even though it could be passive. Thereby, it could be conceived that it could extract some of the energy you've lost as heat afterwards. But we're just going to say by construction that you just lose the reservoir system after your operation, and therefore you can extract the heat afterwards by definition. Or there are alternative ways we can kind of get by this little subtlety, but I won't dwell on it much further. Anyways, yeah, so now we'll just see what the optimal unitary operator, or the equivalence class thereof, would be for probabilistic information erasure. So first I'm going to describe some basic majorisation theory tools which I will be using. Hopefully you all attended Oscar's lectures previously, so I don't have to explain much more than necessary. It's a theorem here. So if you have two vectors of real numbers in Rn, their inner product will obey this relation. So A dot B is going to be less than or equal to A dot B, whereby you permute the elements of this vector such that they are all in decreasing order or non-increasing order. And also it's going to be greater than if you have one of them in decreasing order and one in increasing order. The way I would think of this geometrically is it's kind of a combinatorics thing. Consider vector A as some like a vector of just some real numbers, some parameters, and B as just some weighted distribution thereof. So clearly, if you combine the largest element of A with the largest element of B, so on and so forth, this will be, so the sum thereof will be much greater than if you were to pair the largest element of A with the smallest element of B, and so on. It's quite intuitive, I think. And so there's a corollary which follows from this. So consider two sets of vectors, A1, A2, B1, B2, such that A1 is majorized by A2 and B1 is majorized by B2. It follows simply from this that A1.B1 is going to be less than A2.B2 if you order them both in decreasing order, and A2.B2 will be less than A1.B1 if you have this increasing, decreasing pairing. So, yeah. And for a proof, I refer you to this book, Matrix Analysis by Batia. This theorem is, well, this is actually a corollary of a theorem 2.4.2, but That's the reference. Okay, so maximizing the probability of information erasure. Let's see what I actually mean by that. So you can always write the states of the object and the reservoir as this convex combination of projectors. Of course, this will generally not be unique if there's any degeneracy in these numbers, but that doesn't matter because, again, I'm talking about equivalence classes, not unique unitary operators. So then the tensor product will just be given here, which you can just reorder these objects OL, Rn to again be some other decreasing set, Pn, and these psi n's are just the associated projectors, or product projectors here. And then the unitary coupling will just basically be a unitary transformation of these vectors psi n. Okay? Now the probability of, we want to prepare the object O in the pure state phi 1, and we want to maximize this probability. So the probability that after the unitary coupling between object and reservoir, we call that the probability of information erasure. And if you maximize this, you get the maximal probability of information erasure. Quite natural. So you can just basically write this as this object here, so the PNs, which are just given by the initial state of affairs of your object and reservoir. And these are just the probabilities of finding your object to be in state phi 1. And these can just be, these are just vectors of real numbers. So you can just write it as this D product. And therefore by theorem, the theorem corollary I presented earlier, you can just say, well, the maximum probability is just given by when this thing is majorized and also in decreasing order, which will happen when these objects are 1 for the first dr elements and 0 elsewhere. So therefore, the equivalence class of unitary operators which achieve this are given such that for the vector psi m from 1 to dr, they're taken to the vector phi 1 tensor some orthonormal basis in the reservoir. Okay. And minimizing the heat dissipation basically follows the same kind of arguments here. So you can always write the marginal state of the reservoir post-transformation as this object here. So these are this a decreasing vector of probabilities and some projector on some orthonormal bases in the reservoir. Now the heat dissipation, if you remember, was the change in average energy of the reservoir after as.
Yeah, I just want to clarify before you.
Sure.
So
Okay.
It's easy for me to understand because the heat you're talking about is the information loss, KT log 2.
No. Heat. I'm just defining as the change in energy, average energy of the reservoir. That's what I'm saying right now.
Yeah, because quantum mechanics is inherently reversible, so there is no loss as an information, right?
No, well, okay, I'm saying you have your system and your reservoir, you bring them together, unitarily couple them, then you throw the reservoir away. And how much energy have you put into the reservoir, which by construction you cannot retrieve afterwards. This is the framework we're using here. Of course, you can always reverse it, but if you were to reverse it, then your object would be taken back to its initial state, and thereby you have not done anything. You want the object to be prepared in some state, and then you take it away. So how much energy have you put in from some external power source, which we're not taking into account explicitly here, but you could conceivably do so. So yeah, it's basically how much work do you need to effect this state transformation, given the framework that all you have at your disposal is a reservoir initially prepared in the Gibbs state. Okay. Okay, yeah, so again, because trace of the Hamiltonian with the thermal state initially is fixed, the only thing we want to minimize the heat dissipation, you just want to minimize this thing here. And that can be just written as, again, another dot product of vectors as such. So, so the optimization here can be seen as a two-stage process. Let's initially fix this vector here. So then this will, if for a fixed vector r down u, then you just want to make this in increasing order, these vectors lambda prime, and choose them such that the lambda prime increase would be majorized given all possible vectors lambda prime, or these expectation values. And sorry, that's a bit of a mouthful. But basically, the KY-FAM principle says that for a fixed vector RU, this is minimized if lambda prime, these eigenvalues here, are just the eigenvalues of the Hamiltonian itself, and listed in increasing order. Sorry. Yeah, so basically you're taking the largest probability given by this vector and associating with the smallest energy, so on and so forth. And then to maximize it fully, then you just want to find the vector r prime u, where each element is again is a probability given by this thing, and you want to majorize this. So you want to make sure the first one, r prime 1 u, is as large as you can make it. Then given this constraint, maximize the second element of the vector, so on and so forth. And the same arguments as with the probability of information erasure applies. So to maximize this thing, the first one, you basically take the first dr elements, or no, do elements here to 1 and 0 elsewhere. But because of the orthogonality of the unitary transformations, then for R2, the best way that you can majorize is to first take the first do elements to 0, then the second do elements at 1, so on and so forth. So this is a more compact but maybe incomprehensible way of just stating what I just said in words. So that is the equivalence class of unitary operators, which minimizes the heat dissipation. And if you just compare this rule of transformation for minimizing the heat dissipation with maximizing the probability of information erasure, it'll trivially follow that there is no unitary operator which exists simultaneously in both equivalence classes. So there's a complementarity, if you will, between these two goals you want to achieve. So what you could conceivably consider is having some kind of hierarchy of priorities. So what we want to do is say, first we want to maximize the probability of information erasure. And given this constraint, minimize the heat dissipation. And this is in a diagrammatic way of achieving this, with the further subtlety that the marginal state of the object, if it has a Hamiltonian, will be passive as well. As in the probability of being in, say, so first basically here, phi1 is the ground state of the object Hamiltonian. You maximize that probability, and then you ensure that the probability of the other vectors, phi2, so on and so forth, will always be less or equal than the probability of the ground state. Thereby you're also minimizing the work required to perform the state transformation even further. But anyway, so basically you take the initial probability distribution of the total system of object and reservoir, you list them in decreasing order, and then take these probabilities, which are the dr largest probabilities, take them to the state phi1, which you want to prepare your object in, but then the largest one associated with the ground state, second one with the second excited state, so on and so forth. And then the other sets, pi1 down, these have cardinality do minus 1. So these largest elements go to the state phi1, the ground state, but then the state of the object goes from phi2 to phi0, and then the so on and so forth. So then the next one goes to phi2, so say chi2, and the smallest go to the highest energy level. So yeah, maybe we need to kind of look at this diagram more, see what I'm doing there, but I'll just go along. Now, the trade-off relationship, so what I described right now is some kind of maximal, or like the best case scenario. You want to maximize the probability of information erasure and minimize the consequent heat dissipation. But maybe you don't actually want to maximize the probability of information erasure. You just want it to be greater than some quantity here. So this is p phi 1 max minus delta. And delta is some error that you're going to allow for. Now how can you, for any given delta, what is the characterization of the unitary evolution between object and reservoir which minimizes the heat dissipation? Well, there is a algorithm you can construct of sequential swaps, which for a discrete, non-increasing sequence of errors, you'll have a, again, non-decreasing sequence of heat. So there's a trade-off relationship there, and then you can kind of make it continuous by, instead of having swaps, you have some kind of entangling swaps, which, but yeah, let's just look at the algorithm here. And basically the argument why this algorithm works for discrete errors is that if you want to, basically the optimal case requires that the marginal state of the object and the marginal state of the reservoir be diagonal with respect to the basis in which we want to prepare the object in, and respectively the Hamiltonian of the reservoir. So at most, the entanglements you can have will have the Schmidt coefficients be given by these objects here. So more generalized entangled vectors will not be so good. And then you basically say, you can kind of prove that if you have an error given by this discrete sequence of swaps, if you were to achieve the same error with entanglement, because here you have just product vectors, it will dissipate more heat, essentially. So for this, for the discrete sequence of errors, this is optimal. So basically, okay, maybe how much time do I have?
Under 5 minutes.
Okay. Well, yeah. So here's the algorithm, but I think it's better to just look at the. Oh yeah. So here basically seeing he's swapping this phi L, phi M with phi 1 chi I, but to have this continuous change in error and heat, you can just have swap. You replace swap with swap gamma, which has these real numbers there. So you can continuously increase the probability of information erasure and also increase the heat dissipation. But I think it's more constructive to maybe look at a simple example. So consider here the case where the object is maximally mixed in a three-dimensional Hilbert space, and the reservoir is also in a three-dimensional Hilbert space. And these are just the diagonal elements of the density operator for the whole thing. So here I see phi 1 for the object, phi 2, phi 3, and chi 1, phi 2, phi 3, so on and so forth. So this is the initial state. So you have the 1/3 from the maximum mixed thing here, and these are just the eigenvalues of the reservoir states in decreasing order. And what you do is you first swap R2 with this one. See here you have an increased probability of being in the ground state here, but an increased probability of being in the second excited state as, before. Sorry, yeah. And then you keep doing these swaps, so on and so forth, and then you see the errors here are decreasing, but so is the heat. And also in relation to what Oscar said yesterday, maybe I'll just point this out, about the difference in entropy. So if you remember Landauer's principle, you have the von Neumann entropy initially, right, associated with the heat. And if you wanted to minimize the entropy of the object, in this case the optimal case would have been to do a swap operation, whereby, okay, this would be R1 all, but these would all be R2, and these would be R3. But that would require more heat than required if all you want to do is increase the probability of being in the ground state. See, all we want to do is just increase the probability of being in the state phi 1. We don't care about phi 2 and phi 3 so much. So therefore, here, the probability of being in state phi 2 is less than it would have been had we done a swap. And the probability of being in state phi 3 is more than had we done a swap. So we actually have a smaller entropy reduction than we would have achieved with a swap operation. But both give you the same probability of preparing your object in a pure state. So in a sense, what we're doing here, using the language that Oscar said, we're minimizing the min entropy, not the von Neumann entropy. Because what we're doing is we're maximizing the change in the largest probability of the state spectrum, not maximizing the change in its von Neumann entropy. So yeah, basically if all you want to do is prepare the object in a pure state, you don't need to minimize its entropy necessarily to do so. So of course there's a caveat. If you want to fully purify, then obviously you're minimizing the entropy because the entropy goes to 0. But given that if you have a finite dimensional reservoir, you cannot actually perform full erasure, there's always going to be a limited probability, then doing it this way will be more energy efficient than if you were to have, minimize its entropy as much as you could conceivably have done. And yeah, so acknowledgements, blah, blah, blah. Okay, thank you.
Thanks very much, Mohammad. We've got time for one question.
Lunch?
Yeah, the rumbling of stomachs. the coughing of rumbling of stomachs. Okay, let's thank Mohammad again and all the speakers for